Hello, my name is Michael Balazia. My colleagues are Happy, François Bremond and Dantcheva, and we are from INRIA, Sophia, Antipolis in France. Today I'll be presenting our joint work on biometric uniqueness in the context of face recognition. While face recognition has been widely accepted, we still lack the understanding of uniqueness or distinctiveness of face as a biometric modality. It is worth knowing how environments of similar people impact on difficulty of face recognition. In this paper, we define a uniqueness measure and study the impact of different factors such as image resolution, dataset size, feature extraction algorithm, gender, and age. Uniqueness is one of the 5 major properties of a biometric, along with universality, permanence, measurability, and user-friendliness. It is defined as the ability of a biometric to distinguish between people. To understand the difficulty of recognition using a specific biometric, it is useful to quantify this ability. Andy Adler quantifies uniqueness in terms of biometric information as the decrease in uncertainty about the person's identity due to biometric measurements. Takahashi shows that this biometric information can be approximated by the Kullback-Leibler divergence of genuine and impostor probability distributions. Genuine distribution is given by the comparison scores of observations of the same person, and impostor distribution is given by the comparison scores of observations of different people. We have a high uniqueness if the distributions are well separated, and the uniqueness is low if they significantly overlap. Let's assume a dataset of people and their observations. Each person splits this dataset into the sets of genuine and impostor observations. Naturally, there are more impostor observations than genuine. For the purpose of the algorithm, we select a subset of impostor observations of size 1 less than genuine. Now let's take G as a genuine observation and define the following 2 deltas. Genuine delta of G represents the mean Euclidean norm between G and all remaining genuine observations. Impostor delta of G represents the mean Euclidean norm between G and all impostor observations. See that the cardinality of sample impostor observations and the cardinality of genuine observations without G are the same. We estimate the KL divergence by the average norm estimator defined here. After sampling the impostor observations to exactly G-1, their equation reduces into this, which is now straightforward to calculate. Almost there. Recall the dataset S of C people and their observations as subset S1 to SC. At this point, we just take the equation from the last slide and plug in SP as genuine observations and S without SP as impostor observations. Divergence of the whole dataset is simply the average divergence of a person. And finally, we used sigmoid normalization to fit the domain into the interval between 0 and 1. This is the definition of uniqueness of the whole dataset. We use 4 publicly available datasets. AT&T is a small one with strict laboratory conditions. LFW is a large and wild with thousands of people. IMDb is huge with millions of images and also wild, plus it has annotations of age and gender, which allows us to do specific experiments. We'll also use the twins dataset as it is rather small and not so wild, but it contains people that are very similar to each other, which adds another level of evaluations. First set of evaluations is with fixed face image resolution of 224. We evaluated the 4 datasets on 6 feature extraction algorithms: VGG Face, VGG16, ResNet, Inception, MobileNet, and DenseNet. All of them are trained on ImageNet except for VGG Face, which is trained on faces. Overall best is VGG Face, mostly because of the specificity of the training set. Note also the differences in uniqueness between individual datasets. NT80 is the smallest with laboratory setup, so face recognition is intuitively easier. As the size of the dataset grows, the uniqueness drops. Also, our definition of uniqueness correctly estimates the difficulty of face recognition among twins. Second set of evaluation is with fixed VGG face algorithm, and we observe change in uniqueness depending on image resolution. As a positive surprise, with reduced resolution, we observe only a negligible drop in uniqueness. Third and fourth set of evaluations are to investigate the impact of uniqueness by limiting to a single gender and a specific age group. Here we use IMDb dataset as it has the necessary annotations. Leftmost columns in both visualizations show uniqueness on the full dataset, and all right columns show uniqueness on a subset of it. First thing to notice here is that, as expected, uniqueness of the full dataset is higher than any other subset, even though the subsets have significantly less people and observations. This experiment confirms our intuition that recognizing a man among other men and a person in their 50s among other people in their 50s are more difficult problems than recognizing people in general. To conclude, we introduce a new uniqueness measure of a biometric dataset to estimate the difficulty of recognition of the underlying environment. We study the impact of image resolution, gender, age, dataset size, and feature extraction algorithms. All of them affect uniqueness to a reasonable extent, except for image resolution with only minor impact. In the future work, we will look into the relations between uniqueness and entropy, and would also like to explore how unique is face compared to other biometrics such as iris, gait, or fingerprint. Thank you for your attention.